Okay, so what we have given enough of a kind of a trailer of what is to come. We've spoken about the conjugate direction method. Conjugate direction method, again to revise, what was the essential point? There were two requirements apart from the fact that A is symmetric, positive, definite. What were the two requirements? First one was to do CDM, what do I need? I need a set of conjugate directions. That was the first requirement. Second requirement, I am doing exact line search. So the step lengths are coming from exact minimization. As long as I do this, what were the good things that happened? I got convergence in at most n steps. Okay, so we got a very nice method that if the size of the problem is n, in at most n steps, I will reach the solution. Then what did we find as the main problem in this method? It's a lot of expense. It's computationally expensive to evaluate the conjugate vectors, right? The one clear strategy we found was evaluate the eigenvectors. The eigenvectors were clearly conjugate vectors with respect to A. That did the job for us. But evaluating the conjugate vectors, evaluating the eigenvectors is order n cube. We do not want to spend that price. So that is why the CDM method remained stuck for a while until people came up with something very simple and very clever, which is the conjugate gradient method. So we'll study that now. Okay. So the clever thing about the is called CGM now is that the conjugate vector at the kth iteration depends on the residual at the current state, okay, and some constant times the previous direction. This is in a nutshell the clever idea of the CGM, that instead of asking you to pre-compute the entire set of conjugate directions beforehand, it's saying use the previous conjugate direction pk minus 1 and the current residual, and there is some factor of, this is a scalar factor, which we will choose very, very cleverly. Okay, this is one. Now this is sort of the first ingredient of the conjugate gradient method. The second is, well, you can say it's kind of like, how do I know what is, so what do I need to know to start this algorithm then? I need one P naught, right? Now if I want to pick one P naught, and then so it seems to me that it seems like the recipe is get first P naught and then the next one will be P1. So in the absence of anything else, P naught is chosen in a somewhat obvious way, which is minus R0. Why minus R0? What is the significance of R0 or the residual? It's the gradient, right? So P0 is in fact what? The steepest descent. So in step 1 of conjugate gradient, I do what I already know, which is steepest descent with exact line search. I can't go wrong, right? I will decrease the function value somewhat. And then the subsequent P's, I don't have to do anything expensive. You see what I need, if I need to figure out some formula for beta, Rk is essentially what? Axk minus b. So obviously I know where I am, so I know xk. So axk minus b is not that difficult to evaluate, so I know Rk, right? Now how do I, so this is basically it, you know, this is the conjugate gradient method, and it seems almost like magic because we haven't proved right now that the set of directions are conjugate, right? But we will see, all of that comes out, but the CGM is just this. So let's see, how do you choose beta k? We want to sort of enforce this conjugate property, right? Conjugate, so let's recap over here. What did conjugacy, right? What did it tell me? Pi transpose A Pj is equal to 0, I not equal to j, right? I have an expression here in expression 1 that has pk and pk minus 1, right? So if I wanted to extract out beta from here, what would be the logical thing to do? Using this conjugacy property, left multiply by, okay, left, should I left multiply by pk transpose A? If I left multiply by pk transpose A, I'll get something on the left hand side, but my beta k term will go to 0, right? So if I left multiply by pk minus 1 transpose A, what will I get? I'm going to get, okay, so let's write it in one shot. So left multiply is going to give you pk minus 1 transpose A pk is equal to minus rk, oops, sorry, pk minus 1 transpose A rk plus beta k pk minus 1 transpose A pk, right? Now I want conjugacy. Remember, beta is still in my hand. I can choose it the way I want, right? So it's a free parameter. So I choose, if I want to choose this to be so such that I get conjugacy. So I'm going to insist that this guy go to 0. If this guy goes to 0, what am I left with? Beta k. Beta k therefore has to take on this value, pk minus 1 transpose A rk pk minus 1 transpose A. Right. So what has this ensured? That if I choose, for example, beta 0 according to this formula, okay, so we have started our P0 is minus R0, very good. I made the first step using conjugate gradient method. I reached from x0 to, where did I reach? X1, because I know the step length also, there's a closed form expression. Now I want to calculate P1 and I use this formula, I have the expression for beta, I'll get P1. Am I guaranteed that P1 and P0 are conjugate? Yes, right? That's how I chose my beta. So P0 and P1 are conjugate. Similarly, when I go to the next step, P2 and P1 will be conjugate, right? So we are at least showing that immediate vectors are conjugate with respect to each other. We are not showing that P2 is conjugate with respect to P1 and all other P's below it. That will come later. But the good news is it turns out to be so, okay? Just by this very clever choice of pk, okay? So before we go into details, a little bit of just, what this expression kind of means. The steepest descent was using only minus rk. Pk was minus rk, that was steepest descent. But here what am I doing? There is the immediate short term gain term, which is minus rk, and there is a term from the past. So this is what is somehow giving this method a much more, what should you say, long term view of the solution approach as compared to your steepest descent, okay? There is an analog of this in the gradient descent method also, attributed to one of the gods of optimization called Nesterov, and he invented this thing called the accelerated gradient method, which basically keeps track of current iteration and the previous iteration to give you a faster update, okay? So I'll give you a short brief on that. Yeah. Does bk change at every step? Have a look at the expression. Beta k obviously depends on every iteration. It's not a fixed beta. Okay. Of course, you know that, the way to go to the next remains the same. And the expression for alpha k is also here, rk transpose pk, pk transpose A. Okay. So notice that in order to progress in this conjugate gradient method, what are the computational things that I need to do? I need to evaluate the alpha, I need to evaluate the pk. These are the two things I need to evaluate. To evaluate alpha, what do I need to calculate? There is A times pk, which is a matrix vector product. There's one matrix vector product. Then it is a vector-vector product. Numerator is one vector-vector product. How many vector-vector products do I have so far? Two vector-vector products and one matrix vector product. Similarly, for calculating beta, what do I need? I need, yes, so this is one matrix vector product, this is one matrix vector product, right? So total two matrix vector products, and then followed by two vector-vector products, right? This is what I need to do, just keeping track of the cost involved, right? As I mentioned earlier, if you have a way of evaluating a matrix vector product without storing the matrix A, that works very well for very large problems. So without storing the matrix A, there are some routines which allow you to just evaluate the product of a matrix into vector. So we keep track of the number of these products. Okay. Now this looks like the most basic version of conjugate gradient. It is actually possible to simplify these expressions a little bit more, okay, which is the more commonly found version of the conjugate gradient method. So I'll just outline some of it, and then you will see the even simpler form of the conjugate gradient method. Okay. So rk plus 1 minus rk, what is the definition of r? Is ax minus b, right? So this becomes a xk plus 1 minus xk, right? The b's will cancel off. Is xk plus 1 minus xk anything nice? Alpha k pk, right? So this is alpha k a pk. Okay, this is one thing that you have. So I'm just going to write down the final expression that you get from here. The final expression that you get for alpha and beta, alpha k turns out to be rk transpose rk divided by pk minus 1 transpose a pk minus 1. Okay, what was the original expression is here on the top. So what has changed? The numerator has changed from rk transpose pk to rk transpose rk. Denominator, I think I made a mistake. This is still here. Okay, this is my alpha k. Similarly, I'm going to write down the expression that you get for beta k. It's a particularly nice expression. Okay, so do you see any advantage of this expression, these expressions over the previous expressions from a computational point of view? How many matrix vector products do I need? Alright, so there's only one matrix vector product, and how many vector-vector products? Right, the numerator of alpha k and beta k are the same, so that's 1. Then I have in the denominator one more, right? Is there anything else? How many vector-vector products do you see? 1, 2. I claim there are only 2, because I'm going to store these values, right? So rk minus 1 transpose rk minus 1, I will get from the previous iteration, right? So actually this is just one vector-vector product if I'm doing it cleverly. Okay. So what should I store? Remember, pk is minus rk plus beta k pk minus 1. Okay. So to get this, what all do I need? To get pk, I need rk, I need pk minus 1, and to get beta k, what else do I need? Rk minus 1, right? Rk minus 1. So if you give me Rk, pk minus 1 and Rk minus 1, I get my pk completely. So I know pk. What is left for me to go to xk plus 1? I need a step length alpha, right? And the expression for alpha, do I already have it? Look at the expression for alpha. Once I get pk, do I have alpha k? I have it already, right? So the good news is that as I'm going from iteration to iteration, I don't have to store the entire history. What do I need to store? Current iteration, previous iteration, right? Everything you can see, the subscripts are either k and k minus 1. I don't need to store starting from 0, 1, 2 up to all of that. So what is that telling you? That if my size of the matrix is 1 million by 1 million, I don't need to keep a history of 1 million residuals and the p's, right? All I need is current iteration, previous iteration. So this is why it's also a very, very powerful method. There is no elaborate history to be kept, so it's computationally fast. It's also memory-wise very efficient. There's no unnecessary storage required over here. Okay. Any questions on the basic flavor over here? It seems almost too easy, right? But it's one of those very elegant, clever results in optimization that came about. Okay. Now, unlike in the steepest descent method where we proved the rate of convergence, this time we are not going to prove the rate of convergence. I'm just going to state it. Turns out that the the conjugate gradient method also has a linear rate of convergence. Okay, so yes, at most n steps, right? No, this is telling you at what rate it is happening. Right? But remember that when I say, it's a little bit misleading to say that both the steepest descent and conjugate gradient method have linear rate of convergence. The coefficient of that rate is going to be different from method to method. So one coefficient can be 1, another coefficient can be 100, right? So you will still see the methods progressing at a different speed, and we'll see that later in this lecture when we open up MATLAB, okay? But the rate of convergence in the order notation is still linear, okay? So this is being stated without proof, okay? There are some more very interesting properties. Yes, question? Do we have two vector-vector calculations? Which are those? First is RK transpose RK. Second is PK transpose multiplied by APK. And the second, oh, right. Yes, he's right. There are actually two vector-vector products. I don't have to calculate RK minus 1 transpose RK minus 1 because that was already stored. He's right. There are two vector-vector products. Okay. Now, apart from just saying that it has linear rate of convergence, there are some interesting, rates over here, which we'll just have a look at the analysis of it. Okay. So let's assume A has. Remember, we said that it converges in at most n steps. So that's very tempting. That at most n steps means, can it be faster than n? So there is a theorem which tells us when it can be faster than n, which is again very nice linear algebra. So let us say that I have eigenvalues of ordered in this form. Okay. When I write it like this, obviously these lambdas may or may not be distinct. They can be repeated also. We know that eigenvalues can get repeated, but the eigenvectors will still be orthogonal. Okay, so keep that in mind. Now for a positive definite matrix, the condition number, how can I write it? Lambda, what is lambda max? Lambda n. Okay. Max to min. Okay, this is the condition number. Okay. Now, if I know the eigenvalues of A, let's take two cases. Okay. One is, oops. given some big fat matrix A, I mean not fat, square matrix, but given a big matrix A, I need not know its eigenvalues. I mean, if I know its eigenvalues, you've already given me a lot of information about it. But let's say I don't know the eigenvalues, that is one case. And the other case which is more useful for analysis is, okay, let us say I give you the eigenvalues. So let's just look at the rate of convergence in both cases. You'll see something very surprising. Okay. So what you have is that at the k plus 1th iteration, so I'm looking at this, the distance between where I am and the solution. Okay. This turns out to be okay. So it's depending on the eigenvalue. So can we try to make sense of this? I mean, when do you think this will make a difference? The hint is at most n steps. So can you see if it is possible for us to make sense of this expression? So let us say I have repeated eigenvalues. Okay. So let us say the first 5 eigenvalues are distinct, and then I have the remaining 5 are repeated. Okay. So there's a system with 10 eigenvalues. First 5 are distinct, next 5 are repeated, and they are the same. So what is this telling us? Is it telling us in that in what will happen in what will happen to the rate, or the convergence is because but lambda 1 is still the same, right? So if your what if your smallest eigenvalue is repeated? If your smallest eigenvalue is repeated, then what's going to happen? So let us say the smallest eigenvalue is repeated 5 times. Okay. So so the at if I take k equal to 1, so this is what will I see over here? On the left hand side, I'm going to be looking at x2 minus x star. Over here, what will I see? Lambda, let's say n is equal to 10. Okay. What do I see? Lambda 9 minus lambda 1. Right? Lambda 9 minus lambda 1, is it 0? It's not 0. The first 5 eigenvalues are repeated, right? So this is fine. It is some number. Now, as the iterations go, supposing I reach where k equal to, supposing I reach k equal to 5. At k equal to 5, what happens? I'm looking at distance of x 6 minus x star. Okay. What is the expression I have over here? Lambda 10 minus 5 is 5 minus lambda 1. I have 5 repeated eigenvalues to start with. What is lambda 5 minus lambda 1? Right, 0. So boom, by step 5 at k equal to 5, x 6 minus x star is less than equal to 0. So if I have repeated eigenvalues, that's where this at most n steps result gets invoked, that in fact you can have sooner convergence, and we can also look at that in the case of MATLAB. Okay. So this is of course when I know the eigenvalues of A. Any questions or doubts on this? Was this analysis clear? Okay. Now if I don't know eigenvalues of A, but obviously you need to tell me something, and let us say that something that you're telling me is the condition number. Okay. So I need the same expression that I had, but now in terms of condition number. So what you get is xk plus 1 minus x star turns out to be So now whether there are repeated eigenvalues or not, I really don't, it doesn't enter into this expression, I just don't know it. So does this look familiar from the case of steepest descent? In the case of steepest descent, I had almost the same expression with the change that instead of root kappa, I had, what did I have? Kappa, right? In steepest descent, root kappa was not there, I had actually kappa, right? So this is why the, even though it's a linear rate of convergence, this quantity is going to die down at a faster pace. Okay, so this is why, you know, this is an important aspect of it. So this is just information, I haven't proven it in any way. Okay, but both of these things we will visualize it when we open up MATLAB in a few minutes. Okay. Now we haven't actually proven the entire set of conjugate vectors to be, I mean the vectors to be conjugate with respect to each other, but we can do some, I'm going to show you two interesting properties which are there, right, for the conjugate gradient method, which get used a lot. Okay, so the first one is, this sort of confirms the intuition that we had, that every time you make progress in the kth direction, you never revisit it. This is kind of again quantification of that the error at the kth step is perpendicular to the error in all previous steps. This is what this statement is saying, right? If you replace, again as I said, replace math by English, R is representing residual, which is representing error. Error at the kth step is perpendicular to error at all previous steps, right? And this is surprisingly easy to prove. If you take our expanding subspace theorem, what was the statement of this expanding subspace theorem? Can someone remind me? Rk transpose Pi is equal to 0 for I belonging to in 0 to k minus 1. Okay. What is the definition of Pi? By now we should know Pi is equal to, so the way to remember it is, Pi is, if I didn't know anything, I would do gradient descent. If I did that, Pi would be equal to minus Ri. You got the first time right. Then I said, hey, we are doing something a little smarter than gradient descent, which is to remember something about what? Previous direction. So there should be a Pi minus 1 and there should be a beta here, right? So it's very intuitive to remember this expression. So if I now left multiply, and this was true, okay, this is true for all I, right? So now if I left multiply Rk transpose over here, what am I going to get? Rk transpose Pi is equal to Rk transpose, what did I do? Sorry, Ri plus beta I Rk transpose Pi minus 1. Okay. This term is 0 by the expanding subspace theorem. So I get 0 is equal to okay. Anything else? What about the second term on the right hand side? Also 0 by the same theorem, right? So it implies that Rk transpose Ri is equal to 0, I belonging to 0 to k minus 1. Okay. So there are lots of these very small results you will find in the case of the conjugate gradient method. The ingredients are very few. It's like a khichdi with very few ingredients. What are the ingredients? There's an expression for beta. How did we derive that expression for beta? Here, just by taking the initial definition of pk and demanding conjugacy. I want conjugacy. This gives me an expression for beta. I have one expression for beta. I have one expression for alpha, right? And that's basically it. Everything else just follows from here, some amount of algebra, and I land up with this interesting expression. Okay, there are several other such expressions that are used. For example, when I showed you the simplified version of here, these simplified versions, they also come just by using these simple algebraic identities. Okay. So now what we'll do is we'll have a look at a code implementation of conjugate gradient method. Okay, and we'll sort of have it race against steepest descent, and let's see what happens. Okay, so before we go to that, is there any difficulty here so far in the expressions?